First of all, thank you for all the previous presenters. They covered both the supplementary cementitious material and also machine learning, and that really helped me to just delete 80% of my presentation slides. So let me just focus on the remaining 20%. So I'd like to start my presentation with the plot at the left side. So this plot is based on a large concrete data set comprising more than 10,000 concrete mixtures at different strength levels. And so when we classify them based on the amount of supplementary cementitious material used, we can see that there's a systematic reduction of the concrete cost because of the use of SCMs. And even without changing the strength, we can achieve far better or far lower cost. And when we switch to the side of the carbon embodiment, we can see a more significant reduction. So basically, in terms of both cost and the carbon embodiments, we can really benefit a lot from the use of SCM. So this is the best news that I have for you today. From this point, things may only get worse. Not only will I tell you about the challenges that we are facing for using different type of SCMs in concrete production, but also I will talk about how we can use machine learning techniques to address the challenges that we are facing. So what we experienced over the past few years is a sharp decline in the flash production. And flash is, by the way, the most produced SCM that is used for replacing cement in concrete. And so the wind down of the thermal plants really reduced availability of different flashes. And this, in turn, put a higher requirement for us to determine or make a better determination of the reactivity of different flashes. And on the other hand, we also have many other type of SCMs available. But the problem is that even for those another type of SCMs, we do not have either not enough knowledge to use them, and also they exhibit a large variety from case to case, or even within the same type of material. So in our study, what we really hope to achieve is enable a meaningful screening for the use of different type of SCMs in concrete production. And so by seeing the meaningful screening is not only about the accuracy of the techniques, it's also about the timing of the technique. So I would like to take a moment and review the origin of the flash reactivity, which is the network topology of the calcium aluminate silicate glass. And this can be broadly applied to another type of SCMs. So basically, over the past 10 years, what researchers discovered is that the reactivity of flash is encoded in the atomic structure of flashes, and we can simplify this atomic structure into a truss system. And in taking a step further, we can even use a single parameter called topological constraint per atom to describe the reactivity of different flashes. And this is what you are seeing at the right side of the screen. So we can find that there's a fairly robust correlation between the dissolution rate, which is a direct indication of the reactivity, versus the topological constraint. So this is great, meaning that we can potentially rely on the topological constraint to infer the reactivity of different SCMs. However, it turns out that it's fiendishly difficult to measure the information that we need to calculate the topological constraint, which even in the laboratory environment, measuring the amorphous content of SCMs are not very easy. And back to reality, what we have from the real production or the job set is much simpler testing technique. For example, the XRF for testing the bulk composition of the raw material. So neither of those two techniques can be used for enable us for this kind of rapid screenings. And basically, we do not have the right tool to achieve what we want to get. And this is what machine learning jumps in, and it can be very helpful. And the rationale is that based on the previous study, we know that there are certain correlations between the bulk material composition and their amorphous content. And here, the next slide shows you how we want to approach this rapid screening. So basically, from the job set, we can get a raw material, and by conducting simple and rapid tests such as XRF, and then we extract that information and further couple it with a machine learning model that we developed. And so literally within seconds, we can make a better decision in terms of how we want to make the best use of the raw material on a per batch basis. So in this presentation, I'm going to show you 3 studies that we carried out to fulfill this kind of hope. And the first one, we are really focusing on the reactivity of flashes. And so basically what we did is that we first collect a large flash database. And so the input of those for each of the sample collected in this database is the bulk composition of different major oxides presented in the flashes. And the output of the data set is the topological constraint of the different samples. And by the way, we calculate the topological constraint based on the amorphous phase information that is available from those literature. For example, can be measured by the QXRD. So then we use a neural network to build up our machine learning model. And in this case, we used 80% of the sample to train our model, and the remaining 15% are used to test the model performance. So basically, what you see on the right-hand side, the orange spot, those are the test sample. And you can see that our model achieved equally good performance on both the training and the test set, meaning that we can use our model to make robust prediction for new type of flashes. And so this is fairly encouraging. And based on this study, we since extended our scope to cover more SCMs. And so in this second study, we built an even larger data set, and now it's comprised more than 250 different SCMs, which can be categorized into 8 different types. And so we still use the oxide composition as or the bulk composition as the input and the topological constraint as the output. And the plot at the right side shows you the actual distribution of the different SCMs that we, or for those data that we collected. And you can see that there's a really large variety of those different compositions. And again, we turn to the model construction. And in this case, we are not using a certain portion, but we are using all the flash materials to train our model. And we use another 6 type of non-flash materials to test the model performance. And the plot at the left is the performance. So basically, you can see that for both the flash and the non-flash samples, our model can achieve fairly high accuracy. And indeed, beyond that, our model can also predict the reactivity of another type of SCMs, and this is indicated by the plot at the right side. So as you can imagine, if we have a new type of SCM appeared on this ternary map, then we can make a prediction. But of course, there are another details involved with the uncertainty, which I'm not going to cover in this presentation. So far, I have talked about the model prediction for both flash-specific samples and more in general SCM samples. But there's still a missing piece in the explaining puzzle of this study, which is that so far we are only relying on data from literature. It would be much better if we can find evidence directly based on experiments, and that's what we did recently for the third study. So here, what we here we conducted an experimental validation, and our sample is shown on the left side, and you can see that it's a variety of different SCM particles embedded in the epoxy. And so we first use the SCM EX to characterize the bulk composition. And for the same sample, we put it in under the solution and use the vertical scanning interferometry to test the surface dissolution of those individual particles. So you can think of it like each individual particle will serve as one data point that we can use for our subsequent analysis. And so after extracting the composition variation of the raw sample into this ternary space, this is what we have. But in this case, you can see that the color bar, it shows the dissolution rate rather than the topological constraint. So it's totally separated from what we did from in the first two studies. But what you may also notice is that we also have the bulk material composition for the data that we actually measured from the lab. And we can use those information as the input for our trained machine learning model and predict their topological constraint. So in the plot at the right side, we put the measured dissolution rate on the horizontal axis and the predicted topological constraint on the vertical axis. So in this plot, you can see that there's a clear correlation between the two, and indicating that our model can be used to infer the real reactivity of those different type of SCMs. And actually, if we put the two ternary graphs together head by head, what we will observe is that there are certain samples that is overlapping with the samples that we collected from the literature. And so after mapping those matched samples, this is what we observe. And you can see that actually there are many existing SCMs that can be reliably interpreted or predicted by our machine learning model in terms of their dissolution rates. So this is basically provide us a strong indication in terms of what we want to achieve, which is inferring the reactivity of different type of SCM based on the bulk composition, and that can be used so that we can use this technique in the real production. But in taking a step back, what is the mission critical here? And I think it may be this. So machine learning and AI techniques, especially under this large decimation of the flash supply, is not only an optional research approach that we can take for studying flashes, but also it's really enable us to make meaningful contribution to the use of many other type of SCMs for the production of sustainable and low carbon concrete. So with that, I will conclude my presentation, and now I'm happy to take any questions. Thank you very much.
Thank you very much, Dr. Flong. Very meaningful research. All right. Any questions from the audience on site and online? Questions? Okay. All right. Just a quick comments. I think your research is very useful, very promising for real applications. Okay. Good job, Dr. Song.
Thank you.
All right.